Hello. So now we will continue our presentation. This is the fourth video. Last time we quickly end due to some interruption, and we ended with the introduction to linear maps. And last time we have the notion of basis and dimension, and we ended with the theorem relating the dimension of the sum of vector spaces, that is the dimension of the sum is equal to the dimension of the vector space one, the subspace. The dimension of the two subspaces is equal to the dimension of the individual subspaces minus the dimension of the intersection of these two subspaces. So we just consider two subspaces. For exercise, you may consider the exercise in the book on the dimension of three subspaces. So today, we will go back to what we have started. So the definition of linear maps. So let's start. So let's define a linear map. A linear map, or in other books, it's called a linear transformation, is a function from vector space, a function t from vector space V to vector space W. So here, from now on, we will consider our letters V and W be vector spaces with the following properties. The first property is additivity. So if we have U plus V, U plus, say, okay, U plus V, this is just equal to T of U plus T of our V for all U and V in our vector space. Our vector space V. And then we have homogeneity. We have the linear map, the transformation of the lambda times U, or say times V, is equal to lambda times the linear map T applied to V for all lambda in our vector, our field, and for all V in our vector space V. So remark, so linear transformation is the other name. Name of linear map. Sometimes sometimes we write T of V or T of V. So for this is for notation. And then we define another notation. We have the set of all linear maps from V to W is denoted LVW. Then now we go to examples of linear maps. Of course, we have the first one, 0, is an element of the linear map from V to W. So this 0 is defined, 0 V is just a 0. Here, our 0 is our linear map. The 0 on the left side uh is a function from V to W, whereas this is the 0 here is the identity in W, and then what identity? Additive identity. Here 0 is 0 map, and here V is element of our vector space V. These are trivial example. These two. So the other one is I is an element of the linear map from V to V. So what does I do? I maps V to self. The third non-trivial example is consider the vector space or the linear map from the polynomial with coefficients in R, then polynomial with coefficients in R, and then D here, and then D is differentiation. Now we have the differentiation of our function P is just P prime, where this is the property is that we have Fg is equal to the differentiation or the derivative of F plus the derivative of G, or this is just F prime plus G prime. This from calculus. And also, if we have lambda F, we get lambda derivative of F, which is just lambda times F prime. So the first one here is differentiation. And then we have the fourth, we have integration. Let's call it T. So T here is integration. And then T is an element of the set of linear transformation from T and then to R. Here the polynomial over R. And then here we have the set of real numbers. Let me write this as over or with coefficients in R. And of course, this is defined as follows. This is just the integral from 0 to 1 of p of x dx. Okay. So that's it for the set of linear maps. And then we get some more nice examples that will motivate the general notion of linear map from Fn to Fm, m not equal to n. So we get a linear map T from the set of linear maps from F infinity of from R2 to R3 to R2. And then T of an element X, Y, Z in R3 is defined to be this one. 2x minus y plus 3z. And then 7x plus 5y minus 6z as second component. So this is again a linear map. As you should verify. Now we go to a theorem on the basis and the relation of linear maps and basis of the domain. So suppose that we get a basis V1 to Vn is a basis for our vector space V, and W1 up to Wm, let's fix the same size, is a basis for our V or of V. Then there's a unique linear map T from V to W such that your T of Vj is equal to W sub j for each j from 1 to n. So yeah, we're going to prove this one, and then consider a structure on the set of linear transformations. But first, it's nice to prove this. So for the proof, the first part is the existence of linear map with the desired property. So remember, if you can't follow the proof while I'm discussing it here, it might be good to repeat it again, or like pause whenever you want and then look at what I'm writing. And then if this makes sense to you, then you continue by just playing again, just continuing watch. You can pause whenever you want. So first part is the existence. So we first define our T from V to W. And then here we get an element of our V, which is a linear combination of the bases. This one, Cn, Vn, where our Ci's are in F. This is just equal to C1, W1, up to Cn, Wn, where Ci's are element of our F. Okay? So since V1 to Vn basis, T is function. That is, it's a well-defined function from V to W. So we are okay with doing a function. Now, why? Because every element of V can be written uniquely as linear combinations of elements of bases. All right. So now for each C sub j, taking C sub j equal to 1 and other sys 0, we get T of V I is equal to W J. So if U and V are in the vector space V with U being linear combinations of VI's and this U being equal to C1 V1 and up to Cn Vn, we get what? We get the the image or the function applied to U plus V is equal to this map here, CA1 plus C1 V1, and then we end at AN plus CN Vn. Okay, this is Vn. And then applying the property of linear map, we get A1 plus C1, and then T of V1 is then AN plus CN T of Vn. This is just A1 plus C1 and then WJ and then AN plus CN WJ. That means what? No, WN pala. This is W1, this is WN. And then what? We get, we will factor out our A1 and C1. We get A1 W1 plus ANWN plus C1 W1 up to CNWN. And this part here, is just T of U, and then the other one is T of V. That means thus T of U plus V is equal to T of U plus T of V as desired. And now, similarly, if we get lambda in F and V being C1 V1 up to Cn Vn, then T of lambda V is equal to T of lambda C1 V1 plus lambda Cn Vn. So this is just equal to lambda C1 W1 plus lambda Cn Wn. So this is just lambda C1 W1 plus up to Cn Wn. So this is lambda, the linear map applied to our V. So thus T from V to W is a linear map. Now, for the uniqueness part, suppose that T here is from V to W, and T of Vj is equal to Wj from J from 1 to N. Let C1 up to Cn be elements of F. Then Then by the homogeneity, T of C1 V1 is equal to C of Wj, and T of C1 V1 plus Cn Vn is equal to C1 plus Cn Vn, Wn pala. Thus, we have T is uniquely determined by the span of our V1 to Vn. Because V1 to Vn is a basis, then basis of what? Basis of V, then T is uniquely determined on V. Okay? So that's how we prove this first part. So in this second part, the uniqueness, you can just always do the standard technique that assuming the other one, and then have to show that they are equal. But here we make use with the theorem that we have proved earlier, that our unique representation of elements by as linear combination of the bases. Now we go to algebraic operations on the set of linear maps. So we set this as a definition. So suppose that your S and T are elements of this set of linear combination, and lambda in F define the sum of S plus and T as ST of V is equal to S of V plus T of V, and product ST of V as it's not product, but product with respect to a scalar. Okay, this is just lambda and then T of V. This is for all V in our vector space V. So I will just make it as an as exercise at home, but you need that you may want to verify that S plus T and lambda T are linear maps, given that S and T are linear maps too. Now, because we have scalar multiplication here, and because we have vector addition here, we may make it as a corollary or a theorem that L V to W is a vector space with operations defined above. Okay? And then we have S So the proof here uh is routine, and then I'll just have some remark. In vector space, we do not have assumption of the multiplication or product of two elements, but in some vector spaces, they make sense. For example, this set of linear transformation is a vector space, but we can define here also product of two elements of vector spaces. Product of two elements of this LVW, and then not assume in vector spaces your products. Yung products natin are not assumed, but here in we get products of S and T being just S and T. This is composition functions. Okay, so this is like a nice vector space. So we get now a theorem of properties. Properties of linear maps. So when I say properties, we get, I'll just algebraic properties. Number one is associativity. That is T1, T2, T3 is equal to T1, T2, T3, regardless of your grouping. And then the identity, you have Ti is equal to I, T is equal to T. And then here, I is the identity map on W. This I here, the second I, oh wait, I2, and then I1. And then we have distributivity. Of S1 plus S2 T is equal to S1 T plus S2 T, and S T1 T2 is just S T1 plus S T2, where E1, T2, S1, S2 are the elements. Okay, let me, and T are in the space of linear map from U to V, and then S1, S2, and S are in the space of linear map from V to U. No, not U, but W, because we have a map here, so a composition of maps. Again, because these are just the same long proofs, I will not be discussing the proof of this. Let me refine this definition here. And then S T from L U to V and S from L V to W. And ST is just an element of the linear map from U to W, defined as ST of U is equal to ST of U for all U in U here. Okay. Now we will go to some theorem. So the first one is T is a linear map from B to W. Then the 0 of V is mapped to 0 of W. The proof is as follows. We have T of 0 is equal to T of 0 plus 0. And then this is just T of 0 plus T of 0. And then if you add negative of T of 0 on both sides, we get T of 0 is equal to 0. All right, that's it for our linear maps. Now we go to the subspace of a special subspace of B and W. We this is null space and ranges. Now we first define what's a null space. Okay, for a linear map T from V to W, the null space, or in other books, it's called the kernel of T, denoted null T, is just equal to the subspace, a subset of V that is mapped to 0 by T. All right. So remark in some reference, null T is denoted ker T, or kernel of our transformation T. Okay, we get our some examples first. Okay. T is 0 map. That is T of V is equal to 0 for all V in V. And then T here from V to W, then the kernel, then our null space T is equal to the entire space V. Okay. So another example, if we have this linear map from C3 to F, C3 here is just ordered triple of linear of only ordered triple of complex numbers. And then this is the map is defined as Z1, Z2, Z3. It's just Z1 plus 2Z2 plus 3Z3. Then the null space of our this is equal to the set of triples in C3 such that your Z1 plus 2Z2 plus 3Z3 is equal to 0. So how do you do that? So a basis for the null space of this one is negative 2, 1, 0, and then negative 3, 0, 1. And then why is this a basis? So let's leave this as an exercise. Look at Z1. This is okay. I will just leave it as an exercise. Okay. An important theorem, T from V to W. Now T is a subspace of V. The proof here is easy. And then P of 0 is equal to 0. So 0 is in the null of P. P of U plus V is equal to P of U plus P of V is equal to 0 plus 0. And this means that U plus V is in the null of T given U and V in null T. And lastly, E of lambda V is equal to lambda E of V, which is lambda times 0, which is just 0. So lambda V is also in null T if our V is in the null T. Hence, null T is a subspace of V. Now we define an injective linear map. It's not a linear map, but let's generalize this to a function. Function T from V to W is injective, or is an injection, or is one-to-one if TU equal to TV implies that U is equal to V. So some words are one-to-one, injection, and something like that. And then contrapositively, U V implies T of U is equal to T of. All right. Now we go to an important theorem on injectivity and null space. The theorem is important. So E here is a linear map from V to W. Then E is injective or one-to-one if and only if your null space of T is just trivial or consists of just zero vector only. So let's do the proof. The proof is two direction. So we will suppose T is injective. And then we want to show that the null space is zero. Okay? We know that zero here is in the null space T because this is trivial. So we want to show the reverse inclusion. Suppose that V is in the null space of T, then T of V is equal to 0, which is also equal to T of 0. Since T is injective, then we get V is just 0. Thus, the null space of T is just consists of the 0 vector. Now, suppose that our null of T is just 0, and then we want to show that our T is injective. Okay, suppose our U and V are elements in vector space B, and then T of U is equal to T of V. Then 0 is equal to T of U minus T of V because they are equal. That means that via the proper linear map, T of UV, and thus ang ating U and V, U minus V is an element of null T, null T. Since null T is just 0, is just consists of 0 vector, we get U minus V is just equal to 0. That is U is equal to V, hence T is injective. Okay, so we have shown both directions. Thus, T is injective implies that the null space T is injective if and only if 0 yung ating now we go to range and surjectivity. We define range or image. So a range T is a linear map from V to W. Range T is equal to the image of V, where V is an element of the vector space. This is also known as image of T. We set two examples. of range. Again, I am uh, dodging some computational examples here. If you get the zero map, then zero map from V to W, you get the range of T is just the zero in W. And then the theorem is that T from V to W and range T is subspace of W, and the proof is similar with the one that we have earlier. And then we have a definition a function T from V to W is surjective, or sometimes called onto, if range of our T is equal to the entire space, our entire codomain W. And then, yeah, that's it for our range and images together with the subspaces associated to them. Next time we will continue with the fundamental theorem of linear maps, and then we will go to matrices. Again, we will not be computing matrices or product and sums of matrices here, and a lot of computations. We will be focusing more on the theoretical aspects. So I believe the computational part to you as exercise or just recall of what you have experienced or like computed before. So I think that ends today's recording.